third contribution is called dispersion interactions. And dispersion has to do with induced dipole in some sense, because neither of the objects have a dipole, and so you could think of them as mutually inducing one on each other. But this isn't the best formulation. The work for this was carried about by Mr. Fritz London, and from that we get the word London dispersion forces, as you may have heard. He used the quantum mechanical calculations that we did a couple parts ago, in which we said we could use second order perturbation theory to find what would be the effect on the electron energy levels if we had just this neutral atom. And from this, he was able to arrive at the constants that go above the r to the 6. I think I called it a d before, but he was able to track down these numbers, and there's a variety of estimates of those numbers. But I think a good point is, what is the word dispersion here? What does that mean? The other terms had some meaning to us. Orientation had to do with the orientation of the dipoles. Induction had to do with inducing a dipole on the other. Why is this called a dispersion interaction? Now, the reason London forces can be called dispersion forces is because what he figured out was, in fact, a dispersion relation. Now, a dispersion relation is an equation that relates the frequency of a wave, here this would be the angular frequency, to its wave number k. Now, k is simply 2 pi over the wavelength, if maybe that's a more familiar representation. So it's effectively relating the frequency and the wavelength. Now, there's a few famous dispersion relations in other contexts that might help clear this up. A great example would be electromagnetic waves or photons, light, right? You can relate the frequency of the light to the wavelength, or the wave number, simply by multiplying by c, the speed of light. A very simple equation, a linear dispersion relation. But we can talk about an even more exciting example. That would be Einstein's famous dispersion relation, that E squared equals mc squared plus pc squared. Energy, mass, speed of light, and momentum. This generally applies to all particles. You know, if they have a mass, this makes sense. If they don't have a mass, this term drops out in the case of a photon. And you say, but wait a minute, how is this a dispersion relation? I don't see frequency, I don't see wavelength. Well, we need two other pieces of information. If we just say E, according to Einstein and Planck's work, is simply equal to h nu, which is the frequency. But why are we writing it like that? We can write it as h bar omega, and then we're taking the 2 pi from angular frequency and putting it under the h, gives us a bar. And from de Broglie, we can write the momentum. Well, the momentum is usually h over lambda, but again, using our 2 pi tricks, we can simply say it's h bar times the wave number k. Hopefully we can see that's an h bar. So plugging these two in, we can clearly see this is a formula now relating the frequency of any particle to its wave number, a dispersion relation. London did exactly this, but relating the energy to the frequency and the fluctuations in the electrons within an atom or a molecule. We'll take a look at those examples in the coming videos.